This kind of summarizes the stuff we talked about at the end, right? We learned how to do synthetic division. And we can use synthetic division, to divide these quotients out. The remainder was significant, right? Here's the synthetic division process that corresponds to long division. What we learned yesterday is that it's kind of odd, but it's useful. The remainder that we get when we divide two polynomials is equal to the value of the numerator evaluated at the zero of the denominator, right? So synthetically, plugging in the -1, right, the zero of the denominator synthetically into that yellow polynomial, what I get in the remainder box is the value of this polynomial when I evaluate it at -1. Kind of weird. Okay, and that's the polynomial remainder theorem. So what's this tell us here? The other thing is the factor theorem. We talked about the idea that if you get zero remainder, then that means that the denominator is a factor of the numerator. Okay, that's the factor theorem. Okay, so if x minus k is a factor of p of x, then we know that the remainder is zero. Those go together. Recall that the zeros of a function, think what they mean. The zeros of a function are the values of the input x, so the places, or values of x, where the function, the output, is zero, right? Where the function has a value of zero. So here is the factor theorem, right? K is a zero of f of x if and only if f of k equals zero. When you see this in math, this is a biconditional statement. When you see something like that, if and only if, it's like a two-directional arrow, right? If you start with the supposition that k is a zero of f of x, then that implies that f of k is zero. Or you could start here. If f of k is zero, that implies that k is a zero of f of x. You can start with either one of those parts of that statement, and the other one always follows when you have an if and only if statement. You'll see probably more of that in college. So we've seen that dividing by a factor always produces a remainder of zero, and so we end up with the factor theorem. There it is. Okay. So what can we do with this? Oh, just a quick reminder. You guys fill in the blanks for me. Polynomial remainder theorem. If a polynomial f of x is divided by x minus k, then what does the remainder theorem tell us? Right? The remainder is the value f of k. That makes sense? If I plug k into the function, that's what I get in the remainder box is the value of the function at k. Give me thumbs on that one. Does that make sense? And that's the whole that's the premise of synthetic substitution or synthetic evaluation. Okay, these are the same thing, right? Synthetic division. Oops, I won't do that. Synthetic division is equivalent to synthetic substitution or synthetic evaluation, just different purposes, but the same process. And then the factor theorem, see if you remember that one. K is a zero of f of x if and only if what? Yeah, there you go. Good. Oh, okay, sorry. I mean, that's true. If and only if k is a zero of f of x, right? So that's what we're saying. K is a zero, meaning if I plug it in, I get zero for the function. If and only if x minus k is a factor, right? So these are the two things that are interchangeable. K is a zero, x minus k is a factor. Those always go hand in hand. Okay? So we can use that to do interesting problems like this guy. Okay. Use synthetic division to show that the number given to the right of the equation is a solution of the equation, and then solve the polynomial equation. Okay, so we've done stuff kind of like this before, right? This was last unit stuff. We solved polynomial equations. How would you guys have tried to solve that equation right there? 4-term polynomial equation. What's the only technique that we had last unit for that? Grouping, yeah. Would grouping work? Thumbs up or down? You can tell, right? It's down.
No.
It's down. How come? I saw a couple thumbs down. People, thumbs downers. How come? Yeah, the coefficient test fails, right? Remember the coefficient test. The ratio of the first two coefficients has to equal the ratio of the last two coefficients, and it's not. 2 over -1 is different than -5 over -2, so it fails the coefficient test. If it passes the coefficient test, it still has to pass the variable step-down test, right? That's what we called it. The variables have to step down by the same amount in each group also. They do that, right? The variables diminish by 1 in each of the two groups, but the coefficient test has failed. So we know that grouping cannot work here. So last unit, we would have been out of luck. Nothing we can do. But now we have some more ammunition. We're trying to, they give us a hint here. They say use synthetic division to show that the number given, that's 2, is a solution. How would we do that? Okay, so what am I going to put in? You guys help me out with my synthetic division process here. What am I going to put out in front? I'm putting 2, right? Right, because I want to show that the number given is a solution. If it's a solution, why would that go out front? If it's a solution, try to connect those dots. It being a solution means I put a 2 out front, but why?
You have to put back into get back the same polynomial.
Say it again. Say that one more time. I think you were on the right track. Just say it again.
It's what you have to put back in to get the same, like if you take it out, you have to put it back in to get the same polynomial.
Okay. What is the, let's go back and look at see if any of these theorems are useful to us.
Was it the substitution to synthetic division thing?
I mean, kind of. What about this factor theorem?
Just k minus 2 is 0.
Yeah, 2 is a 0 of the,
What were you saying?
like 2 is a 0 of the equation.
Okay,
and that's why-
if 2 is a 0, right, then x minus 2 would have to be a factor, right? Doesn't that make sense? And so if it's a factor, then really the zero product property would tell us that's a solution, wouldn't it? Right? Does that make sense? Okay, so if this thing goes in, like it's a factor, if I could divide in x minus 2 with no remainder, then we know it's a factor. Factors go with zeros. So all we'd have to get, the test would be, what would have to happen in my remainder box here? When I run this 2,
0.
I'd have to get 0, wouldn't I? Right? If I get 0 remainder, then that tells me that 2 is a 0 of this function. And so it's a solution, right? Isn't that what we're looking for? Are all the values of x that make this function right here equal to 0, right? Okay. So what do I need in the top row of my synthetic bracket? Tell me the numbers. And that's what we're looking for, is the remainder. Okay, so what do I get? If I do the process here, what do I get?
Carry the 2.
Okay, carry 2 down.
Multiply the 2 by 2.
Okay, add them, good. So I get 3.
6. Positive 1. 2. 0.
And 0. Okay, so we just verified it, right? The fact that we get 0 there means that this is a solution, right? 2 is a solution. Okay. What's that do? How's that help me? I'm trying to solve the polynomial equation, so I need all the solutions, not just that one. How am I going to get all those other solutions from? Okay, so x minus 2 is one of my factors, right? When we were solving polynomial equations, we used grouping, but that was just a technique for accomplishing our goal of factoring the polynomial, right? If I could factor the polynomial, then I could apply the zero product property and find all my solutions, right? So my goal here was to write this function as something to break this up into a product of factors. Well, one of my factors I know, what is it? X minus 2, right? X minus 2. I get that from the fact that I know 2 is a 0. If 2 is a 0, X minus 2 is a factor. That's what the factor theorem tells us. If K is a 0, then X minus K is a factor, right? Okay, give me thumbs. So far, is this making sense? Is our logic flowing? Okay. Questions? So you can ask questions. If you're not sure.
I wasn't here yesterday.
Oh, okay. If you weren't here yesterday, this would be kind of mysterious. Yeah. Okay, so then we need the other one, right? Well, how do I find where's the other factor going to pop out? Right, I'm trying to break this up into pieces. 2x squared plus 3x plus 1, isn't it? Right? Because if I divide my original polynomial by x minus 2 and I get no remainder, and this is the outcome, that's the other factor, isn't it? Everybody see that? Right? So in other words, let's write that down here. Right? So if I get my original polynomial, 2x cubed minus x squared minus 5x minus 2 divided by x minus 2 equals this guy, right? 2x squared plus 3x plus 1. Well, isn't that the same thing as saying if I multiply each side by x minus 2, isn't that the very same thing as saying that this is equal to x minus 2 times 2x squared plus 3x plus 1, right? Okay, so dividing this out synthetically and getting 0 remainder is the same thing as factoring it, isn't it? Right? Because factoring is just division. When I factor something out, I'm just dividing it out, right? Okay, so now what? That gets us going, right? That kind of broke free the logjam there, and we couldn't factor by grouping, but now the fact that we were given that hint to try to and it worked, now we should be able to finish this up. What else do I need to do? Yeah, I got factor that green trinomial. Okay, so what would my magic numbers have to? I'm going to group that, right? What would the magic numbers that I'm going to split 3x up into? What would they have to multiply to and add to? Multiply to 2, right? Good. They're going to multiply to the outside product. So my magic numbers, m times n, would have to equal 2 times 1. And they'd have to add to the inner coefficient, right? Add to 3. So what are they?
2 and 1.
2 and 1. There we go. So we can split this guy up then into 2x squared plus, doesn't matter, plus, we said they're 2 and 1, right? Plus x plus 2x. That's how we split our 3x up, our magic numbers, 1 plus 2, like that, right? If I factor by grouping, what do I get out of my first group here? X times
X plus
2x plus 1. And if this is my plus sign that's joining the two groups, oops, the other group is just 2x plus 1. Right? We're almost there. Let me scoot this stuff down a little bit. Now what? What can I factor out with my x minus 2? What can I factor out of the green brackets?
X.
Yeah, there's a common factor. The 2x plus 1 is common to each term, so I can factor that away, right? That guy goes out front. And then what's left behind? Yeah, what's left behind? I've got a coefficient of 1 there, right? So what's left behind is x plus 1. Everybody good with that? That last part? That's just kind of last unit stuff. Give me 1 to 5 so far. How we doing? Okay. So now I've got it fully factored. What are my solutions? 2.
-1/2.
Yeah. Right, so now we got all 3. Knowing one of them allowed us to get all 3. Okay, so this is kind of as far as we can go with this process right now. We'll look at one more example. I'll show you another little technique that's kind of handy. But later on, I want you to see a roadmap for where we're going to go with this by the end of the year. So we want to be able to, like, we relied on them to give us, first of all, well, one thing, we're at this point, we're not really, we haven't focused on techniques for solving quadratic equations. I mean, we've a little bit. The only technique we've really looked at is solving quadratics, like all polynomials, by factoring. So we will come back later, and we're going to dive into just polynomial, or just quadratic polynomials. There are some techniques, and you guys have seen these in the past. Like, you've used the quadratic formula before, right? So you guys, it's been a while, but there are some other methods for solving a quadratic equation. Like if we're trying to set this factor equal to 0, 2x squared plus 3x plus 1, we could complete the square to solve that. We could use the quadratic formula. If we're dealing with quadratics that only involve x squareds, we can use the square root property where we isolate the x squared and square root both sides. So there's some other things we'll look at that will make it easier for us to solve these, find the zeros of these quadratic factors in the process. We'll get better at that. The other thing we'll do is we're not going to rely on the generosity of the math gods to give us a value to try. We'll come up with a scheme for actually picking the values that would make sense to try. They may not all work, but it's called the rational root theorem, and we can come up with a list of all the possible rational number zeros that a polynomial could have. And then we'll just kind of whittle those down and find some that work. And so that we do have some purely analytical techniques for dealing with this stuff, but we're just not quite there yet. So for now, we're just taking small steps to get there. Okay, what about one like this? This is a little different. Factor f of x, given that k is a 0. Okay, now this time they're telling us k equals -2 is a 0, and the multiplicity is 2. Okay. So how could we factor this thing completely if we know that -2 is a 0 with multiplicity 2? What are some ideas? Kind of similar to what we did last time, right?
Yeah, can't you just do synthetic division because you have a 0?
Okay, I could. Yeah, that'd be probably the easiest way to do it. I know that k is a 0, that -2 is a 0, and I know it's a 0 how many times? Twice. Okay, so I could just do repeated synthetic division. Now there's a way to do that. I'm going to show you a couple ways. Maybe I'll just show you. I'm not going to do the whole full tabular synthetic division yet because that'll make more sense to do with rational root theorem. But I will show you how you can nest successive synthetic division processes, right? So you can just do this. We know this is a 0. We know -2 is a 0, so we can set up a bracket. What goes in my top row of my bracket? 1, 3,
3, -2, -172, -1. I don't like how big these numbers are.
Those are big numbers, yeah. Okay, we already know what we need to get in that remainder box. What is it?
0.
0, yeah, we know it's 0 because we're told that. K is a 0, right? So we know we've got to get a 0. If we don't get a 0, we're screwed up. We better go back and find our mistakes. It has to be 0, right? What goes out front? Whoops, -2, yep. Okay, so what does that give us if I go through the process then? 1,
-2, 1, -2, -4. I can't see the board. 80, positive 80.
Go positive 80.
I don't know that part.
190 or 176.
Where are you getting
What?
hundreds from?
160.
negative what?
64.
Negative
No.
90.
Oh.
I don't know.
84.
There you go. And
That's, wait. Yeah.
It'll be it, let's just call it it.
hey, what do you know? 168. Okay, it worked out, right?
You got
Okay,
there.
got it. Okay, so what we can do now, check this out. Here's a way we know that synthetic division has to work twice. So look what we can do. We can just take this and go like that, can't we? Right?
Wait,
Make sense?
We're back to negative.
Okay.
That's a negative, yep.
Because now think what this implies. If the multiplicity is 2 of this factor, that means that I need to be able to divide my polynomial by x plus 2 twice, right? And it should work both times. So I divided once and I got this reduced polynomial, but I know I've got to be able to do the same thing again because the multiplicity is 2. So what do I get if I do that? And again, what number goes out front? -2. There we go. What do I get if I do this process? 1.
-2, -1, +2, -42,
Positive 80.
0.
So it works, right? Okay, so then that tells me quite a bit, right? That tells me that this polynomial is equal to what factors? Product of what factors?
Is it x minus 2 squared?
X plus 2 squared, right? Everybody get that? Okay, because the multiplicity is 2. So times,
X squared minus x minus 42.
there you go, times that. X squared minus x minus 42, right? And that we're trying to factor this thing. That's all they wanted us to do was factor it. And so we could probably go one step further. We got a basic trinomial. What are the magic numbers here?
-7, +6.
-7, +6. There you go. So we get
Y2K.
done, factor, okay? What's our other plan? So that's, to me, that's the best way. But how could we use long division here?
Only one thing about
Wouldn't you just like put that thingy in there and then divide it by x plus 2?
Okay, I could, but if I'm going through the hassle of long division, I probably don't want to do it twice. So with long division, what would I do?
a lot.
Just not do long division.
Not do long division. But how could I use it? Just theoretically, because there may be a time when you have to. What could you do?
X squared plus whatever the next number is.
So we could divide by, we know that the multiplicity is 2, right? So we already know that x plus 2 squared is going to be a factor. So we could just expand that out and divide our original polynomial by that expanded quadratic trinomial, right? Everybody see that? Okay, this would be like, there will be cases where this is something we're going to have to do when we eventually get further on and we're talking about quadratics in more detail and we start to talk about non-real numbers. Then we're probably going to want, like, what if we knew that, I guess it won't make any sense to you guys, if we knew that like 1 plus I and 1 minus I were non-real zeros, we can't really divide those through synthetically very conveniently. So then we'd have to find the product that we get of the factors that give us those zeros and divide it through using long division. So there will be, my point is just that there will be times when we'll need to do it this way, when synthetic division won't be a viable alternative. Okay, so we could just divide through using long division. This is what goes inside, right? Man, look at where that room. I'm gonna go to the next page. We need more room.
Yeah, I said Monday, Tuesday, Wednesday I have a contest, Thursday I have a track meet.
No, they were in vision.
And then Friday I have.
Okay, here we go. Back to it. So, one more time. So we get x to the fourth plus 3x cubed minus 42x squared minus 172x minus 168 goes inside. What's going to go outside? Ah, okay, good. X squared, keep going.
Plus 4x.
Plus 4x. Right, because remember, can we distribute the exponent there? No, we can't, because those are being added, right? We have to use the pattern. We're just using the pattern a plus b quantity squared is what?
A squared plus
2ab plus b.
There we go. Okay, so that gives us x squared plus 4x plus 4. Okay, so that's what goes outside. Okay, so what do we get if we do that? First term, x squared. X squared goes into x to the fourth, x squared times, I distribute, right? X squared times this whole polynomial gives me x to the fourth plus 4x cubed plus 4x squared. And we'll do this the best way. We'll just put it all in parentheses and subtract out front. So if we subtract vertically, what do we get? You know, they cancel, obviously, first terms. What do I get here?
Negative x cubed.
Negative x cubed.
Negative 38x.
Remember, I'm subtracting.
Oh, negative 46.
46, there you go. Bring the rest down. Okay, we go again. Now what? X? Negative x. Good. How many times does x squared go into negative x cubed? Negative x. Distribute that through. I get negative x cubed minus 4x squared minus 4x. I'm going to subtract vertically. Those guys cancel. Now be careful, I'm subtracting. What do I get here?
Negative 50x squared.
No.
Negative 42x.
Negative 42. How about here?
160.
Good. Okay, and one more time. What do I get this time?
Negative 42.
Yeah, I got negative 42x squared divided by x squared. Gives me negative 42. If I run that through, I get negative 42x squared minus 168x minus 168. What do you know? What's our remainder?
So 0.
0, as we knew it had to be if we did things correctly. Okay, so again, we got the same thing we got before, right? We get this, which is just x plus 2 quantity square times the orange polynomial is what we started with, right? So very same outcome that we had before. Okay, then we just factor that just like before. Okay, make sense? Okay, so you could go either way. I mean, that's probably not the preferred way of doing it. If there's any advantage to that, the only advantage is at least you only had to divide once, right? But synthetic was easier, yeah. All right, why don't you guys try one of these on the boards, and then I'll turn you loose. Try that guy, go.